I'm glad to attend this conference. Today's topic I want to talk is Geographic and Temporal Deep Learning Method for Traffic Flow Prediction in Heavy Network. We will illustrate our work from the following 5 aspects. The aspects are shown up here. The first section we talk is background about our work. The photo on the right screen is a map of Henan province. From the photo, we can see clearly that the Henan highway consists of heavy network and toll stations. The purpose of our work is to predict daily traffic flow of all toll stations in entire heavy network at one time, so that Henan Heavy Management Department can better manage and operate their highway. Obviously, each toll station on the heavy network has temporal features. For example, for a specific toll station, there will be a fixed vehicle commute on working days. On weekends or holidays, the traffic flow will increase due to people's travel needs. In addition, each toll station also has special features. Because each station belongs to this heavy network, vehicles entering from any toll station may leave from a specific station. In order to improve the prediction accuracy of traffic flow, we analyzed many popular methods to deal with traffic flow prediction. Then we found that these methods have some shortcomings. The first one is lacking of consideration of the complex spatial temporal dependency of traffic flow at heavy toll stations. And the second weak point is lacking of consideration of the impact of external features on traffic flow. Therefore, to overcome these shortcomings, our method extracts the mapping relationship to the traffic flow from 3 aspects, which is shown up at the bottom of the screen. These features are spatial features, temporal features, and external features. External features include extreme weather such as heavy rain, storm, and blizzard, and calendar types which is used to classify weekday and weekend. At this section, I describe our method proposed in a paper, GTM, Geographic and Temporal Model. It can be divided into several stages. First stage is feature extraction. It includes construction of heavy network and extraction of temporal and external features from raw data. The second stage is feature engineering, which is used to extract special temporal features of traffic flow by graph convolutional network and long short-term memory. Besides, the external without any processing during this stage, as you can see on the screen. Then the third stage is feature concentration. During here, we concentrate all features including special temporal features obtained by Xing and LSTM, and external features from feature engineering stage. The final stage is a linear stage. In here, we use 3 for connection network to train relationship among all features and transform the output channels into certain dimension that made the problem to tackle. From here, we introduce each stage of our model in a more detailed way. For the feature engineering stage, the first thing I want to talk is construction of heavy network. Only by constructing a heavy network can we extract the special features among toll stations. Therefore, based on 3 basic constructing principles, we build our heavy network and store it in a way of a JSON list, which you can see on the left of screen, though it is an example of the JSON list of heavy network. At the left of screen is principles to build our network. Connectivity rule stimulates that the graph we construct is a connected graph. This rule is in line with the actual situation of China's highway, because in real situation, any point is connected to other points. At the same time, this will also guarantee that we can achieve the traffic flow prediction for all toll stations in highway. Neighborhood rules specifies we will select adjacent toll stations based on the geographic topology of the highway. Bidirection rules ensure that the highway graph we create is an undirected graph. This rule is in line with the actual Chinese highway sense, because any toll stations are bidirectional on the highway network. Besides constructing highway network, temporal feature processing is another important mission during feature engineering stage. In here, we need to decide how long historic time window we need to predict the future traffic flow. From the photo in the middle of the screen, it describes daily traffic flow information from May 8 to 22, 2017. A total of 15 days of traffic flow dates are displayed here. From the photo, obviously we can see a certain pattern, that is, on weekend traffic flow is higher than weekdays. Therefore, to capture this pattern of temporal features, we chose 15 days historical traffic flow to predict future traffic flow. The last thing during feature engineering stage is to obtain external features, including extreme weather and calendar types, so that the prediction accuracy of traffic flow can be improved by our model. Because in extreme weather conditions, the highway will be severely affected and may stop operating directly, resulting in a significant drop in the traffic flow at the toll station. Similarly, during holidays, people have more time to travel, which will lead to an increase in traffic flow at toll stations. In the feature extraction stage, we first use Xing to extract special features from highway network. At the left of screen, there are two lines. A formula of Xing is expressed that we use two-layer Xing to capture special features in our work. In here, A head represents the adjacent matrix of our network. X is a matrix which represents features of every node, as you can see from the photo on the right. So every node have 15 features, which represent historical traffic flow at that node. At the second layer of Xing, the input feature is exchange historical traffic flow for output feature gained by first layer Xing. By stacking two layers of Xing, our model can better learn relationship among all toll stations. At this stage, is another significant thing to extract temporal relationship. So LSTM. 15 LSTM cells are used to extract temporal features. The number of LSTM cells is the same with the size of historical traffic flow window we used. The input for every LSTM cell is the traffic flow of all toll stations on a certain day, which is expressed on here is SV1 to SVD. S represents the traffic flow, V represents all toll stations on highway, and D represents certain day, and the output of the last LSTM is used by us, because it contains all temporal features before that moment. The output of the last cell is represented as HD in the picture. When special temporal features are obtained by Xing and LSTM model, as you can see on the screen, we combine them with external features into new features, which contain special temporal and external features. Then these new features are put into a linear stage. A model learned relationship among all features by three linear layers. Meanwhile, so linear state, the dimension of the feature can be mapped to the same dimension as the problem, and then we can get the prediction result we want. To explain the better accuracy of our model obtained, in the next section we talk about experiments of our model. First experiment is to illustrate the importance of temporal features. There is a line chart at the left of screen. Black line represents the ground truth of traffic flow. Blue and red line represent our model GTM and its variant, without considering temporal features respectively. In contrast, our model GTM fits the ground truth better. Besides, at the right of the line chart, there are two tables. The first table, which is corresponding to line chart, describes prediction accuracy of our model for certain mental station, and the second table describes the prediction accuracy for all toll stations on highway network. For those two cases, a model achieves better accuracy on metrics. The second experiment also uses our model GTM to compare its variance, but this time we are comparing accuracy in different calendar types. We selected 4 days from the test site, of which the 16 and 70 are weekends. These are the leftmost picture and the rightmost picture. The other days, 20 and 28, are working days. From the table below, we can see that the RMS matrix of the model GTM is smaller than its variant model, regardless of whether it is on weekdays or on rest days. This shows that obtaining temporal features so as LSTM is very effective for improving the prediction accuracy of traffic flow. However, in the MAE and MAP matrix, the prediction accuracy of the variant model is better than that of the GTM model. We believe that the prediction accuracy of the two models is at the same level on those two metrics. Therefore, considering temporal feature is important to improve prediction accuracy. Third experiment we have done is to compare prediction effect with other models. We chose two certain toll stations to predict their traffic flow, and the prediction of two toll stations is shown on the screen. You can see from the line chart, the size of traffic flow at Luoyang toll station is less than 10,000. At contrast, the size of traffic flow at Zhengzhou Xiqu toll station is more than 10,000. The reason we chose two stations with different size of traffic flow is to verify our model can get better prediction result in any size of traffic flow. Models we use for comparison include gradient boost regression tree (GBRT), K nearest neighbor (KN), and LSTM. From the table shown at the bottom of screen, we can clearly see that our model GTM get better prediction results among all metrics, including RMSE, MAE, and MAP. No matter the size of traffic flow at certain toll, our model can get better results. At the end of my presentation, there are 3 points I want to conclude. The first one is that the influencing factors considered by our model are more comprehensive, including special temporal features, weather features, and calendar features. The second one is that we use the advantages of JSON to learn special relationship among all toll stations. As you know, JSON can better capture the relationship among all nodes, especially in non-unification space. This advantage is more in line with our real situation-heavy network. In addition, LSTM is an excellent variant of RN, inheriting most of the characteristics of RN models, and at the same time, solving the problem of vanishing gradient caused by the gradual reduction of the gradient backpropagation process. By doing so, we use LSTM to obtain temporal features hidden in historical traffic flow sequence. And the last one is, we comprehensively consider all of these features and get better prediction result, which is verified in a real situation. Thank you for your patience. If you have any questions, please feel free to communicate.